Okay, let's just dive right in. Today, we're unpacking one of the absolutely most mind-bending extreme phenomena in the entire universe, pulsars. I mean, these celestial powerhouses literally defy our everyday understanding of physics and gravity.
So what exactly is it? Well, imagine a massive star ending its life in a violently spectacular supernova. The super dense, spinning core that gets left behind? That's a pulsar. Essentially, we're talking about a highly magnetized, rapidly rotating neutron star.
In this explainer, we've got four main things to hit. First up, the whole cosmic lighthouse effect. Then we'll look at their extreme physical characteristics, figure out how exactly they are powered, and finally, wrap up with some famous pulsars from history. All right, part one, the cosmic lighthouse. Let's talk about those iconic, sweeping beams. Now, here's where it gets kind of weird. A pulsar's rotation axis is usually completely out of whack, totally misaligned with its magnetic axis. So it's shooting out these ultra-narrow, highly focused beams of electromagnetic radiation right from its magnetic poles. And because of that tilt, those beams don't just point straight in one static direction, they're whipping all over the place as the star spins. And honestly, that sweeping motion is exactly why we call them the lighthouses of the universe. The star spins with that misaligned axis, the electromagnetic beams physically sweep across empty space, and here's the cool part. If Earth happens to be directly in that sweeping path, our telescopes pick up this perfectly regular pulse of energy. The star isn't actually turning on and off like a light switch. The beam is just sweeping past our line of sight over and over again. Moving on to section 2, extreme physical characteristics. Prepare to have your mind a little bit blown by the scale of this. Okay, picture our sun. Massive, right? Now imagine taking 1.5 times the mass of our entire sun and crushing it, literally cramming it into a sphere that is only 20 kilometers wide. That's roughly the size of a single city like London or New York. The sheer, unimaginable compression forces you'd need to make that happen, it's just wild. To put that crazy density into an everyday perspective, if you were to somehow scoop up just a single tiny teaspoon of pulsar material, it would weigh roughly 1 billion tons here on Earth. 1 billion tons. That is basically the equivalent of taking the entirety of Mount Everest and squishing it down to fit on a piece of silverware. Oh, and they're definitely not just sitting there. Your run-of-the-mill pulsar spins maybe once a second. But millisecond pulsars, they can rotate up to a dizzying 716 times per second. Let that sink in. An object heavier than our sun, whipping around hundreds of times faster than you can even blink. And as if the spinning wasn't chaotic enough, these tiny powerhouse cores are wrapped in magnetic fields that are literally trillions of times stronger than the magnetic field we have here on Earth. They're basically cosmic dynamos, churning out some of the absolute most powerful magnetic forces in the entire known universe. But here's the real kicker. Despite all this insane, violent chaos, a pulsar's rotation is profoundly stable. We're talking so perfectly stable that it rivals the extreme accuracy of our best atomic clocks. Because of that jaw-dropping precision, astronomers absolutely love them. We use that perfect timing as a tool to test general relativity and even detect the super subtle ripples of gravitational waves rolling across the cosmos. All right, section 3, how pulsars are powered. Let's look at what's actually fueling all this intense activity. So astronomers generally break these down into 3 categories based on where they get their juice. First, you've got your rotation-powered pulsars. These guys simply lose their rotational energy as they gradually, slowly spin down over time. Then you have accretion-powered pulsars. These are the ones locked in binary systems, practically cannibalizing a companion star by pulling matter right off it, which unleashes these massive blasts of X-rays. And lastly, magnetars. These are powered entirely by the slow decay of their exceptionally, unbelievably strong magnetic fields. Which brings us to our final section, number 4. Famous pulsars in history. Let's trace a quick timeline of our biggest discoveries out there in the dark. It's so fascinating tracking this from ancient skies to modern astronomy. Way back in 1054 AD, astronomers actually observed the massive supernova that gave birth to the famous Crab pulsar. Then, jump all the way to 1967, and you have Jocelyn Bell Burnell and Anthony Hewish making the groundbreaking discovery of the very first officially recognized pulsar. And today? Well, today we're tracking absolute monsters like PSRJ 1748, which holds that mind-boggling record of 716 spins per second we talked about earlier. It really leaves you wondering, doesn't it? As we keep monitoring these giant cosmic atomic clocks, what other beautiful secrets of the universe are they waiting to reveal? Are they going to unlock brand new mysteries about gravitational waves? Or maybe even fundamentally reshape our entire understanding of the fabric of space time itself? I guess we'll just have to wait and see.